Steven Weinberg's early life and intellectual brilliance cannot be understood simply as the story of a gifted child who became a famous scientist. It is a deeper narrative about curiosity, discipline, historical context, and the gradual shaping of a mind that would later redefine modern physics. Born on May 3, 1933, in New York City, Weinberg entered the world during a period of immense global uncertainty. The Great Depression was still affecting families across the United States, and within a few years, the world would be plunged into the chaos of World War II. These events formed the background of his childhood, subtly influencing the values of seriousness, realism, and rational thinking that would later characterize his scientific and philosophical outlook. Weinberg grew up in a family that valued education and intellectual effort. His parents were not scientists, but they encouraged learning and curiosity, providing an environment where asking questions was not discouraged. From an early age, Weinberg showed an unusual fascination with how things worked. Unlike many children whose interests shift rapidly, his curiosity had a persistent and focused quality. He was not satisfied with surface-level explanations and often wanted to understand the deeper principles behind everyday phenomena. This trait would later become one of the defining features of his scientific style. As a child, Weinberg was particularly drawn to books and self-directed learning. He read widely, especially in science and mathematics, subjects that allowed him to explore logical structures and universal laws. Mathematics, in particular, appealed to him because of its certainty and clarity. Unlike history or literature, where interpretations could vary, mathematics offered proofs and definitive answers. This attraction to logical rigor shaped his thinking long before he formally studied physics at an advanced level. One of the most important influences on Weinberg's early intellectual development was his exposure to popular science writing. Books and articles that explained scientific ideas to a general audience opened his imagination to the possibility that the universe could be understood through human reason. These writings did more than inform him, they inspired him. He realized that science was not just a collection of facts, but an ongoing quest to uncover hidden patterns in nature. This realization gave him a sense of purpose and direction at a young age. Weinberg attended the Bronx High School of Science, one of the most prestigious science-focused schools in the United States. Admission to this school was highly competitive, and the environment was intellectually intense. Surrounded by other highly motivated and talented students, Weinberg thrived. The school emphasized problem-solving, critical thinking, and scientific discipline, all of which suited his natural inclinations. It was here that his interest in physics became more focused and serious. At Bronx Science, Weinberg encountered teachers who recognized his exceptional ability and encouraged him to push beyond standard coursework. He was not merely memorizing formulas, he was learning how to think like a physicist. This meant questioning assumptions, testing ideas logically, and valuing mathematical consistency. These habits of mind became central to his later work in theoretical physics. Another key aspect of Weinberg's brilliance was his independence of thought. Even as a student, he was not easily influenced by authority or popular opinion. If an idea did not make sense to him logically, he was willing to question it, regardless of who proposed it. This intellectual independence later allowed him to pursue ideas that others ignored or dismissed, including his early work on Electroweak unification. After high school, Weinberg went on to study at Cornell University, one of the leading institutions for physics in the world at the time. Cornell provided him with exposure to some of the best physicists and thinkers of the era. However, even in this elite academic environment, Weinberg stood out for his depth of understanding and analytical strength. He was not content with simply mastering existing theories. He wanted to understand their foundations and limitations. At Cornell, Weinberg studied under prominent physicists who were actively engaged in shaping post-war theoretical physics. This was a time when physics was undergoing rapid transformation. Quantum mechanics and relativity had already revolutionized the field, but many fundamental questions remained unanswered. For a young student like Weinberg, this atmosphere was both challenging and exciting. It reinforced his belief that physics was a living discipline, full of unresolved problems waiting for bold ideas. Weinberg's intellectual brilliance was also evident in his ability to connect abstract mathematics with physical reality. Many students struggle with this balance, either becoming lost in mathematical formalism or focusing too much on physical intuition without rigorous structure. Weinberg excelled at combining both. He could use mathematics as a precise language to describe physical laws while never losing sight of the underlying physical meaning. This rare skill later became essential in his work on unifying fundamental forces. Following Cornell, Weinberg pursued further studies at the Niels Bohr Institute in Copenhagen and later at Princeton University. These institutions exposed him to different scientific cultures and styles of thinking. In Copenhagen, he encountered a strong tradition of conceptual analysis and philosophical reflection on physics, influenced by figures like Niels Bohr. At Princeton, he was immersed in a more formal and mathematically driven approach to theoretical physics. Rather than being confused by these differences, Weinberg absorbed the strengths of both traditions. During this period, Weinberg developed the mental independence necessary to work largely alone on deep problems. While collaboration is common in physics, many of Weinberg's most important insights came from solitary thinking. He valued discussions with colleagues, but he did not rely on consensus to validate his ideas. This independence allowed him to explore unconventional paths and resist the pressure to conform to dominant trends in the field. Weinberg's intellectual character was also shaped by a certain emotional toughness. Theoretical physics can be an unforgiving discipline where ideas are judged harshly and quickly dismissed if they fail to meet strict standards. Weinberg learned to separate criticism of his ideas from criticism of himself. This emotional distance enabled him to refine his work objectively and to abandon or revise ideas when necessary without losing confidence. Another key feature of his brilliance was his long-term vision. He did not think in terms of isolated papers or short-term achievements. Instead, he thought about building a coherent understanding of nature piece by piece. This approach required patience and a willingness to delay recognition. It also required faith that the universe is intelligible and that human reason, guided by mathematics, can uncover its deepest laws. By this stage of his life, Weinberg had fully developed the intellectual tools that would later allow him to propose one of the most important theories in modern physics. His deep understanding of quantum field theory, his respect for symmetry, his intolerance for inconsistency, and his philosophical commitment to realism all converged into a powerful way of thinking. These were not accidental traits. They were the result of decades of disciplined learning and reflection. Steven Weinberg's intellectual brilliance, as revealed in this second phase of his early development, was not merely about being smarter than others. It was about thinking differently, more deeply, and more patiently. He combined technical mastery with philosophical insight, historical awareness with mathematical rigor, and personal independence with scientific responsibility. This combination prepared him to take a decisive step that many others hesitated to take: the proposal that two seemingly distinct forces of nature could be unified into a single theoretical framework. While that achievement belongs to the next keynote, its roots lie firmly in the qualities developed during these formative years. In understanding Weinberg's early life and intellectual brilliance as a whole, we see how a great scientific mind is formed. It is shaped by curiosity, strengthened by education, refined by discipline, and guided by a deep belief in the power of reason. Steven Weinberg's journey reminds us that the foundations of revolutionary ideas are often laid quietly, long before the world recognizes their importance. The challenge of unifying the fundamental forces of nature is one of the deepest and most demanding problems in the history of physics, and understanding this challenge is essential to appreciating Steven Weinberg's achievement. To grasp why unification was so difficult, one must first understand how physics itself evolved and why the forces of nature appeared fragmented, incomplete, and even contradictory by the middle of the 20th century. From the earliest days of science, humans sought simple explanations for complex natural phenomena. Ancient thinkers believed that the universe must be governed by a small number of basic principles. This intuition turned out to be remarkably correct. Over centuries, scientists discovered that many different phenomena, motion, heat, light, electricity, magnetism, and chemical reactions, could be explained by underlying laws. Each major advance in physics brought with it a sense of unification, the feeling that nature was not chaotic, but organized according to hidden order. By the 19th century, one of the greatest unifications had already been achieved. Electricity and magnetism, once thought to be entirely separate forces, were shown by James Clerk Maxwell to be two aspects of a single electromagnetic force. This achievement was not only mathematically elegant, but also experimentally powerful. It explained light itself as an electromagnetic wave and revealed that very different phenomena were connected at a deep level. Maxwell's success set a powerful precedent. If two forces could be unified so beautifully, perhaps all forces could eventually be understood as parts of a single framework. However, the 20th century brought both progress and confusion. With the rise of quantum mechanics and relativity, physicists gained unprecedented insight into the microscopic and cosmic realms. At the same time, new forces were discovered that complicated the picture. The strong nuclear force was identified as the force that holds atomic nuclei together, overcoming the repulsion between positively charged protons. The weak nuclear force was discovered through the study of radioactive decay, a process in which particles transform into other particles in ways that seemed to violate classical expectations. By the mid-20th century, physicists recognized four fundamental forces: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. Each force appeared to operate according to different rules, act over different ranges, and involve different particles. Gravity governed planets and galaxies, electromagnetism governed atoms and chemistry, the strong force governed nuclei, and the weak force governed radioactive processes. The dream of unification seemed increasingly distant. Among these forces, the weak nuclear force was especially troubling. Unlike electromagnetism, which could be described by a clean and consistent mathematical theory, the weak force resisted simple explanation. Early theories of the weak force worked only at low energies and broke down at higher energies, producing infinite results that made no physical sense. These mathematical failures were not minor technical issues. They suggested that the theories were fundamentally flawed. This situation created a crisis in theoretical physics. Physicists knew that their descriptions of the weak force were incomplete, but they did not know how to fix them. Some believed that the weak force was fundamentally different from other forces and might never fit into a unified framework. Others suspected that a deeper theory existed but could not see how to construct it. The challenge was not only scientific but conceptual. It forced physicists to rethink their assumptions about what a successful theory should look like. One of the key obstacles to unification was the problem of mass. Electromagnetism is mediated by particles called photons, which have no mass. This masslessness explains why electromagnetic forces have infinite range. In contrast, the weak force acts over an extremely short range, implying that its force, carrying particles, must be very massive. However, introducing massive force carriers into quantum field theories led to mathematical inconsistencies. The equations became unstable, and predictions lost their reliability. This created a paradox. To explain the observed properties of the weak force, its carriers needed mass. But to maintain mathematical consistency, force carriers needed to be massless. Reconciling these two requirements seemed impossible. Many physicists concluded that unification with electromagnetism, which relies on massless photons, was unrealistic. Another major challenge was symmetry. Symmetry plays a central role in modern physics, describing how physical laws remain unchanged under certain transformations. Electromagnetism is based on a powerful symmetry principle that ensures charge conservation and mathematical consistency. Extending this idea to the weak force was extremely difficult. The weak force behaves asymmetrically, distinguishing between left-handed and right-handed particles in ways that seem to violate the symmetry principles that worked so well elsewhere. This asymmetry shocked physicists. For decades, symmetry had been regarded as a guiding principle of nature, almost a law in itself. The weak force appeared to break this principle, suggesting that nature might be fundamentally lopsided at a deep level. If symmetry could be violated so dramatically, how could it serve as a foundation for unification? Experimental limitations further complicated the challenge. Testing theories of the weak force required extremely high energies, far beyond what early particle accelerators could achieve. This meant that many theoretical ideas could not be directly tested, leaving physicists unsure which paths were promising and which were dead ends. The lack of experimental guidance made the theoretical landscape even more uncertain. The challenge of unification was also psychological. After decades of success, physicists were accustomed to steady progress and clear solutions. The stubborn resistance of the weak force undermined this confidence. Some researchers became cautious, focusing on small, incremental problems rather than bold unifying ideas. Others pursued speculative theories but struggled to gain acceptance within the scientific community. Despite these difficulties, the desire for unification did not disappear. It was driven by a deep philosophical conviction that nature, at its most fundamental level, should be governed by simple and coherent principles. This conviction was not mere aesthetic preference. It was supported by history. Time and again, apparently complex phenomena had been revealed as manifestations of simpler underlying laws. To abandon the search for unification would mean abandoning one of the most successful guiding ideas in science. Steven Weinberg entered this intellectual landscape at a critical moment. He was fully aware of the failures and frustrations that surrounded the weak force. He understood why many physicists were skeptical of unification and why the problem seemed nearly impossible. Yet he also shared the conviction that the laws of nature must possess a deeper unity. For him, the challenge of unification was not a reason to retreat, but a reason to think more boldly and carefully. Weinberg recognized that any successful unification would need to preserve the mathematical strengths of electromagnetism while explaining the unique features of the weak force. It would need to account for massive force carriers without destroying consistency, and it would need to incorporate symmetry in a more subtle way than previously imagined. This required not just new equations, but a new way of thinking about how forces and particles relate to one another. The challenge was enormous because it demanded a balance between imagination and discipline. Too much imagination risked producing theories detached from reality. Too much discipline risked trapping physicists within existing frameworks that could not solve the problem. Navigating this narrow path required intellectual courage and a willingness to accept temporary uncertainty. In this sense, the challenge of unifying fundamental forces was not merely a technical problem. It was a test of the scientific world. You itself. Could human reason penetrate nature's deepest structure? Could abstract mathematics reveal truths about forces too small to see directly? Could symmetry, despite its apparent violations, still serve as a guiding principle? By the time Weinberg began formulating his ideas, these questions had no clear answers. The unification of the weak and electromagnetic forces seemed to many like an unattainable dream. Yet it was precisely this atmosphere of difficulty and doubt that made the eventual breakthrough so significant. The challenge lay not only in solving equations, but in reshaping the conceptual foundations of physics. It required physicists to accept that forces could appear separate at low energies while being unified at higher energies, a radical idea at the time. It required trusting mathematical consistency even when experimental confirmation was far away. And it required patience, as recognition and validation would not come quickly. During these formative years, Weinberg developed a clear sense of what he believed good physics should be. For him, a successful theory had to be mathematically consistent, experimentally testable, and conceptually simple. He believed that nature, at its deepest level, is governed by elegant principles, even if those principles are difficult to discover. This belief guided his research choices and gave him the confidence to pursue ambitious unifying ideas. Weinberg's early brilliance was not limited to raw intelligence. It also included extraordinary discipline and patience. He was willing to spend long periods thinking deeply about a problem, refining equations, and reconsidering assumptions. He understood that major breakthroughs rarely come from quick insights alone. They require sustained effort and careful reasoning. This mindset distinguished him from many of his peers and prepared him for the long and often lonely path of theoretical innovation. Equally important was Weinberg's emotional relationship with science. He did not view physics as merely a career or academic pursuit. He saw it as a calling. Understanding the laws of nature gave him a sense of meaning and fulfillment. This deep emotional commitment helped him persist through periods of doubt and lack of recognition later in his career. By the time Weinberg completed his formal education, he had already developed the core qualities that would define his scientific life: intellectual independence, mathematical mastery, conceptual clarity, and a deep belief in the unity of nature. These qualities did not emerge suddenly. They were the result of years of reading, studying, questioning, and thinking deeply about the world. Steven Weinberg's early life demonstrates that great scientific achievements are rarely the product of talent alone. They emerge from a complex interaction between individual curiosity, supportive educational environments, historical circumstances, and personal discipline. His intellectual brilliance was not just a gift. It was something he actively cultivated through hard work and critical thinking. This foundation would later enable Weinberg to tackle one of the most difficult problems in modern physics: the unification of fundamental forces. The confidence to propose such a theory, and the resilience to stand by it despite early rejection, can be traced directly back to his early years. His childhood curiosity, his rigorous education, and his independent mind all played essential roles in shaping the physicist who would eventually change our understanding of the universe. Steven Weinberg's intellectual brilliance continued to deepen as he transitioned from being a student of physics to becoming an independent thinker capable of contributing original ideas. This phase of his life marked the transformation from learning established knowledge to questioning it, refining it, and eventually extending it. The habits he had developed in his early years, rigorous logic, independence of thought, and patience, now began to show their true power. As a young researcher, Weinberg entered a scientific world that was both exciting and uncertain. The mid-20th century was a period when physics had achieved extraordinary successes, yet it was also filled with unresolved contradictions. Quantum mechanics and special relativity were firmly established, but their deeper implications were still debated. The weak nuclear force, in particular, posed serious theoretical challenges. It was poorly understood, mathematically unstable in many formulations, and difficult to connect with other known forces. For many physicists, these problems were frustrating obstacles. For Weinberg, they were invitations. One of the defining features of Weinberg's brilliance was his refusal to accept theoretical ugliness as inevitable. He believed that the fundamental laws of nature should be coherent and mathematically consistent. If a theory seemed messy or required artificial fixes, he suspected that it was incomplete. This belief was not based on blind faith, but on historical experience. Again and again, the most successful theories in physics had turned out to be those with deep internal harmony. Weinberg's early professional years involved intense study and reflection rather than immediate groundbreaking success. He held academic positions where he taught, researched, and quietly developed his ideas. During this time, he was absorbing new experimental results, learning from other theorists, and sharpening his understanding of quantum field theory. He was especially interested in symmetry principles, which describe how physical systems remain unchanged under certain transformations. These principles had already proven powerful in explaining electromagnetism and other areas of physics. What set Weinberg apart was his ability to see long-term connections where others focused on short-term calculations. Many physicists were busy solving specific problems or fitting theories to existing data. Weinberg, while fully capable of such work, was more concerned with the overall structure of physical law. He asked questions such as, why do forces take the form they do? Why are some particles massive while others are not? Is there a deeper unity behind the apparent diversity of nature? These questions were not easy to answer, and pursuing them required intellectual courage. At the time, proposing highly abstract theories without immediate experimental support was risky. Academic recognition often depended on producing results that could be quickly tested or applied. Weinberg, however, was willing to invest time in ideas that might take years or decades to be confirmed. His brilliance also showed in his ability to learn from failure. Early attempts by physicists to describe the weak force had run into serious problems, including mathematical inconsistencies. Rather than abandoning the problem, Weinberg carefully studied why these attempts failed. He treated each failure as a source of information, revealing which assumptions were wrong and which directions might be promising. This analytical resilience was a key component of his success. Another important aspect of Weinberg's intellectual development was his growing philosophical clarity. He developed strong views about what science is and what it is not. He rejected the idea that scientific theories are merely convenient tools for organizing observations. Instead, he believed that good theories describe real features of the world, even if those features are hidden from direct observation. This realist perspective gave him confidence that searching for deeper unifying principles was not just an aesthetic preference, but a meaningful scientific goal. Weinberg was also deeply aware of the historical development of physics. He studied how past breakthroughs had occurred, noticing that many revolutionary ideas were initially ignored or misunderstood. Figures like James Clerk, Maxwell, and Albert Einstein had proposed theories that seemed abstract or unnecessary at first, only to later be recognized as fundamental. This historical awareness helped Weinberg remain patient and selfish, or during periods when his own ideas did not receive immediate attention. His brilliance extended beyond pure research into his extraordinary clarity of thought and expression. Even in technical discussions, Weinberg had a reputation for precision and directness. He avoided vague language and preferred arguments that could be clearly stated and logically defended. This clarity made him a formidable thinker and later an influential writer and teacher. It also forced him to hold his own ideas to the highest standards, as unclear thinking had no place in his intellectual framework. As Weinberg matured as a scientist, his confidence grew, not as arrogance, but as trust in disciplined reasoning. He understood that even the most beautiful ideas must ultimately face experimental testing. Yet he also recognized that experiments are guided by theory, and that without bold theoretical visions, experimental progress can stagnate. This balanced understanding of theory and experiment was another hallmark of his intellectual brilliance. One of the most profound difficulties was that forces behave very differently depending on energy. At everyday energies, electromagnetism dominates most interactions we experience, while the weak force appears almost invisible, noticeable only in rare processes such as radioactive decay. This dramatic difference made it seem unreasonable to suggest that the two forces could be closely related. If they were truly unified, why did they appear so unequal in strength and range? This question struck at the heart of how physicists interpreted physical law. Traditionally, forces were assumed to have fixed identities, with properties that did not depend on context. The idea that a force could change its apparent character depending on energy was unfamiliar and unsettling. Accepting unification meant accepting that the distinctions physicists observed might be emergent rather than fundamental, a concept that challenged deeply held intuitions. Another major challenge was the role of mathematical consistency. Quantum field theory, the framework used to describe particle interactions, is extremely sensitive to internal contradictions. Even small inconsistencies can lead to meaningless predictions, such as infinite probabilities. Many early attempts to unify forces produced exactly these problems. The equations worked in limited cases, but collapsed under more general conditions. This created a harsh selection environment for ideas. A theory was not allowed to be mostly right. It had to be perfectly consistent or it was worthless. This level of rigor discouraged speculation and made theorists cautious. The unification of the weak and electromagnetic forces required a theory that could survive the strictest mathematical tests, even before experimental evidence was available. At the same time, the experimental situation offered little guidance. Particle accelerators of the era could not reach energies high enough to probe the deep structure of the weak force directly. This meant that theorists had to work almost blindly, guided by principles rather than data. In such conditions, even well-motivated ideas could not be easily distinguished from misguided ones. The challenge also had a sociological dimension. Physics, like all human endeavors, operates within communities that develop shared expectations and standards. By the 1950s and early 1960s, many physicists had become skeptical of grand unifying ideas. Previous failures had made them cautious, and there was growing respect for approaches that focused on practical calculations rather than deep explanations. Proposing a unifying theory of forces risked being seen as unrealistic or overly ambitious. This atmosphere influenced which ideas were taken seriously and which were ignored. Theoretical proposals that did not immediately connect with experimental programs were often set aside. This created a feedback loop in which bold ideas struggled to gain attention, reinforcing the perception that unification was a dead end. Overcoming this environment required not only intellectual insight, but also the willingness to work in relative isolation. Another subtle challenge was conceptual language. Physicists lacked a clear way to talk about forces that are unified at one scale but distinct at another. The familiar categories of strong, weak, and electromagnetic were based on observed behavior, not on underlying principles. To unify forces, physicists needed new concepts that could describe how apparent differences emerge from a single foundation. This difficulty was closely tied to the problem of symmetry breaking. Symmetry, when unbroken, implies uniformity and equivalence. Yet the physical world is full of asymmetries. Explaining how symmetrical laws could give rise to asymmetrical phenomena was a major conceptual hurdle. Without a clear understanding of this process, unification remained an abstract ideal rather than a workable theory. The challenge was further complicated by the role of probability and uncertainty in quantum theory. Unlike classical physics, quantum mechanics does not provide definite outcomes but only probabilities. Incorporating this probabilistic framework into a unified theory of forces demanded extreme precision. Any ambiguity in interpretation could undermine confidence in the theory's predictions. Steven Weinberg understood that solving these problems required a layered approach. He recognized that unification might not be directly visible at low energies, where experiments were performed. Instead, the underlying unity could be hidden, revealed only indirectly through careful theoretical reasoning. This insight was crucial because it allowed him to imagine a theory that was unified in principle but fragmented in appearance. This idea required a new attitude toward explanation. Rather than demanding that a theory mirror everyday observations, physicists would need to accept that observations might be misleading, reflecting surface effects rather than deep structure. This was a philosophical shift as much as a scientific one. It required trusting abstract principles over immediate intuition. The challenge of unification also exposed the limits of reductionism in its simplest form. While physicists believed that complex phenomena could be explained by simpler components, unification suggested something more subtle. That simplicity might exist at a deeper level than the components themselves. Forces could appear complex and unrelated, yet be manifestations of a single, elegant framework. Another aspect of the challenge was time. Even if a unifying theory were correct, it might take decades for technology to catch up and test it. This raised questions about how science should evaluate ideas in the absence of direct evidence. Should beauty and consistency be trusted, or should theories be rejected until experiments could confirm them? The unification problem forced physicists to confront these questions openly. For Weinberg, the challenge was not discouraging but motivating. He saw the difficulty of unification as evidence that the problem was deep and therefore worth pursuing. Easy problems rarely lead to fundamental breakthroughs. The very resistance of the weak force to explanation suggested that it held the key to a deeper understanding of nature. The challenge also sharpened Weinberg's sense of responsibility as a theorist. He believed that proposing a theory was not enough. It had to be precise, internally consistent, and open to experimental testing in principle. This disciplined approach distinguished serious unification attempts from speculative ones and helped restore credibility to the idea that forces could be unified. As the intellectual struggle continued, it became clear that unification would not come from extending existing theories in a straightforward way. It would require rethinking basic assumptions about mass, symmetry, and interaction. This realization marked a turning point in theoretical physics, opening the door to ideas that would once have seemed too radical to consider. By the end of this period, the challenge of unifying fundamental forces had reached its most intense form. The problem was clearly defined, the obstacles were understood, and the stakes were evident. Either physics would find a way to bring coherence to its description of nature, or it would remain a collection of disconnected models. Electroweak theory represents one of the most profound revolutions in modern physics because it fundamentally changed how humanity understands the forces that govern nature. Before this theory, the weak nuclear force and electromagnetism were seen as entirely separate, unrelated interactions. They behaved differently, operated at different ranges, and seemed to follow different rules. The idea that these two forces could be unified into a single theoretical framework was not only bold but deeply counterintuitive. Yet electroweak theory demonstrated that beneath their apparent differences lies a shared foundation, revealing a deeper unity in the laws of nature. At its core, electroweak theory proposes that the weak nuclear force and the electromagnetic force are two manifestations of one unified interaction. This unified force behaves differently depending on energy conditions. At very high energies, such as those that existed shortly after the Big Bang, the two forces are indistinguishable. As the universe cooled and energy levels dropped, this unified force split into the weak force and electromagnetism, each taking on its familiar properties. This idea introduced a revolutionary way of thinking. Forces that appear separate in everyday experience may actually be unified at deeper, more fundamental levels. One of the most groundbreaking aspects of electroweak theory was how it resolved long-standing mathematical problems. Earlier theories of the weak force produced infinities that made predictions meaningless. These infinities were not minor technical errors. They indicated that something was deeply wrong with the theoretical framework. Electroweak theory solved this by embedding the weak force within a more symmetrical and mathematically consistent structure. This allowed physicists to make precise predictions that could, in principle, be tested by experiments. A central feature of electroweak theory is its explanation of mass. The weak force is extremely short, ranged, which implies that its force, carrying particles, must be very massive. However, adding mass directly into the equations destroyed mathematical consistency. Electroweak theory introduced a subtle mechanism in which particles acquire mass through interactions with an underlying field that fills all of space. This idea was revolutionary because it suggested that mass is not an intrinsic property of particles, but something that arises from deeper interactions. Decades later, experimental confirmation of this mechanism became one of the greatest achievements in physics. The theory also transformed the role of symmetry in physics. Symmetry had long been a guiding principle, but the weak force seemed to violate it by treating certain particles differently. Electroweak theory showed that symmetry is not truly broken at the fundamental level. Instead, it is hidden. The underlying laws remain symmetrical, but the state of the universe does not reflect that symmetry fully. This concept of hidden or broken symmetry became one of the most powerful ideas in modern science, influencing not only particle physics, but also condensed matter physics and cosmology. Another revolutionary impact of electroweak theory was its predictive power. It did not merely explain known phenomena, It predicted the existence of entirely new particles. These particles were responsible for carrying the weak force and had specific properties, such as mass and charge, that could be tested experimentally. When these particles were eventually discovered, their properties matched the predictions of the theory with remarkable accuracy. This level of agreement between theory and experiment reinforced confidence in the idea that abstract mathematics could reveal real features of the physical world. Electroweak theory also reshaped the scientific method in fundamental physics. It demonstrated that a theory could be widely ignored or underestimated for years and still turn out to be correct. Initially, the theory attracted little attention because it was difficult to test and mathematically demanding. Its eventual success showed that patience and trust in consistency can be just as important as immediate experimental confirmation. This lesson influenced how later generations of physicists approached speculative but well-founded ideas. The impact of electroweak theory extends beyond its specific content. It became a cornerstone of the Standard Model of particle physics, the framework that describes nearly all known fundamental particles and forces, except gravity. Without electroweak unification, the Standard Model would lack coherence and explanatory depth. The theory provided a template for how unification might work, inspiring efforts to unify other forces and even all interactions into a single theory. Philosophically, electroweak theory changed how people think about reality. It challenged the idea that what we observe directly reflects the true structure of nature. Instead, it suggested that reality has layers, with deeper laws hidden beneath surface appearances. This perspective encouraged scientists to look beyond immediate observations and trust well-supported theoretical principles, even when they describe realms far removed from everyday experience. The theory also had a profound impact on experimental physics. Testing electroweak predictions required building powerful particle accelerators and developing new detection technologies. These technological advances did more than confirm the theory. They expanded humanity's ability to probe the universe at extremely small scales. In this way, electroweak theory indirectly contributed to technological progress and the growth of scientific infrastructure worldwide. Perhaps the most lasting impact of electroweak theory is the confidence it gave to the idea of unification itself. Before its success, unification was a hopeful but uncertain dream. Afterward, it became a proven strategy. Scientists could point to electroweak theory as evidence that nature truly is unified at a fundamental level, even if that unity is not immediately obvious. This success continues to motivate research into deeper theories that aim to include gravity and explain the universe as a whole. In summary, electroweak theory was revolutionary because it unified two fundamental forces, resolved deep mathematical problems, redefined the concept of mass, introduced hidden symmetry, predicted new particles, and reshaped both scientific practice and philosophy. It showed that nature is more unified, subtle, and elegant than previously imagined. Through this theory, humanity took a major step toward understanding the underlying order of the universe, confirming that even the most puzzling differences in nature can emerge from a single, coherent foundation. The story of initial rejection and eventual experimental proof is one of the most revealing chapters in the history of modern physics, because it shows how revolutionary ideas often struggle for acceptance before transforming scientific understanding. In the case of electroweak theory, this journey highlights not only the difficulty of the scientific problem, but also the human and institutional factors that shape how new ideas are received. When Steven Weinberg first proposed his version of electroweak unification in 1967, the physics community was not ready to embrace it. At the time, the weak nuclear force was widely regarded as an unsolved and possibly unsolvable problem within quantum field theory. Earlier attempts to describe it had failed, producing mathematical infinities that made predictions meaningless. As a result, many physicists had grown skeptical of grand theoretical solutions and were cautious about ideas that lacked immediate experimental support. Weinberg's proposal was highly abstract and mathematically demanding. It relied on advanced concepts such as gauge symmetry and a subtle mechanism for giving particles mass without destroying consistency. To many physicists, this approach seemed disconnected from experimental reality. There were no existing machines capable of testing its predictions, and the theory itself appeared, at first glance, to be just one more speculative attempt among many. As a result, Weinberg's paper attracted very little attention when it was first published. This initial rejection was not due to obvious errors in the theory, but rather to its timing and context. The physics community was focused on approaches that produced quick, testable results. Electroweak theory required patience and faith in mathematical consistency, qualities that are difficult to maintain in a competitive scientific environment. Some physicists also found the idea philosophically uncomfortable, as it suggested that forces appearing very different at low energies could be unified only at energies far beyond current experimental reach. Another reason for skepticism was that similar unification ideas had been proposed before and had failed. Without clear experimental guidance, it was difficult to distinguish Weinberg's theory from earlier unsuccessful models. Many researchers simply assumed that it would encounter the same problems and moved on to other work. For several years, electroweak theory remained largely unnoticed, discussed by only a small number of theorists. The turning point began when other physicists carefully examined the mathematical structure of the theory and realized something remarkable. Unlike earlier models of the weak force, electroweak theory was internally consistent. It avoided the fatal infinities that had plagued previous attempts and allowed precise calculations to be made. This realization gradually changed attitudes as physicists began to see that the theory was not just elegant, but potentially correct. At the same time, experimental technology was advancing. Particle accelerators were becoming more powerful, and new detectors were being developed that could probe higher energies and rarer processes. This technological progress opened the possibility of testing the predictions of electroweak theory, even if indirectly. The theory predicted the existence of specific force, carrying particles associated with the weak interaction, each with well-defined properties. As experimentalists began to search for these predicted effects, evidence slowly accumulated. Measurements of weak interaction processes showed patterns that aligned with the theory's expectations. These early confirmations did not prove the theory outright, but they strengthened confidence in its framework. What had once seemed purely speculative now appeared increasingly grounded in reality. The decisive moment came with the direct experimental discovery of the particles predicted by electroweak theory. These particles were found in high-energy collider experiments and displayed exactly the properties required by the theory. Their masses, interaction strengths, and decay patterns matched theoretical predictions with striking accuracy. This agreement was not vague or approximate. It was precise and quantitative, leaving little room for doubt. This experimental proof transformed the status of electroweak theory almost overnight. What had once been ignored became central to particle physics. The theory was no longer a bold speculation, but a confirmed description of nature. Steven Weinberg, along with his collaborators in the broader development of the theory, was awarded the Nobel Prize in Physics in recognition of this achievement. The shift from rejection to acceptance illustrates an important lesson about how science progresses. New ideas are not judged solely on their beauty or originality. They must survive rigorous testing and scrutiny. Yet the process is not always smooth or fair. Revolutionary theories often challenge established ways of thinking, making them difficult to accept even when they reveal deeper truths. This story also demonstrates the essential partnership between theory and experiment. Weinberg's theory could not have succeeded without experimental confirmation, but the experiments themselves were guided by theoretical predictions. Without a clear theoretical framework, experimentalists would not have known what to look for or how to interpret their results. The eventual proof of electroweak theory shows how progress depends on the interplay between imagination and evidence. Beyond its scientific importance, this journey has philosophical significance. It shows that nature does not always reveal its secrets easily or quickly. Understanding may require trusting abstract reasoning long before direct observation is possible. Electroweak theory taught physicists that reality can be deeper and more subtle than appearances suggest, and that patience is often required to uncover its true structure. The initial rejection of electroweak theory also serves as a reminder that scientific consensus is not infallible. Even well-trained experts can overlook transformative ideas when they do not fit prevailing expectations. This does not mean that skepticism is wrong. Rather, it highlights the need for openness to carefully constructed ideas, even when they seem unconventional. In the end, the experimental proof of electroweak theory stands as one of the greatest validations of theoretical physics in history. It confirmed that abstract mathematical principles can accurately describe the real world at its most fundamental level. The journey from rejection to proof not only secured the place of electroweak theory in science, but also reinforced confidence in the power of human reason to uncover the hidden unity of nature. This episode remains a powerful example for future generations of scientists. It teaches that persistence, intellectual courage, and respect for evidence can overcome doubt and resistance. What begins as an overlooked idea can, through careful reasoning and experimental confirmation, become a cornerstone of human knowledge. Weinberg's role in the Standard Model of particle physics. Explain it in 1,000 words. Steven Weinberg's role in the development of the Standard Model of particle physics is central and transformative because his ideas provided the structure that turned a collection of partial theories into a coherent, predictive framework. The Standard Model did not emerge fully formed from a single discovery. It was built gradually through decades of theoretical insight and experimental testing. Weinberg's contribution gave this evolving structure its deepest unity and explanatory power. Before the Standard Model took shape, particle physics was fragmented. Physicists had discovered a growing zoo of particles through experiments, but there was no clear organizing principle that explained why these particles existed or how their interactions were related. Electromagnetism was well understood, and the strong and weak nuclear forces were known to exist, but each seemed to require a different theoretical treatment. The field lacked a unifying framework that could bring order to this complexity. Weinberg's most decisive contribution was his formulation of electroweak theory, which unified the weak nuclear force with electromagnetism. This unification was not just an isolated success. It became a foundational pillar of the Standard Model. By showing that two apparently different forces could arise from a single underlying interaction, Weinberg demonstrated that unity, not fragmentation, was the correct way to think about fundamental physics. This insight shaped the overall architecture of the Standard Model. A crucial aspect of Weinberg's role was his use of symmetry principles. The Standard Model is built around the idea that the laws of physics are governed by deep symmetries that determine how particles interact. Weinberg showed how these symmetries could be applied consistently to the weak force, which had previously resisted such treatment. His work revealed that the weak force, despite its unusual properties, could be described using the same powerful mathematical language as electromagnetism. Weinberg also played a key role in clarifying the concept of force reminder particles within the Standard Model. In this framework, forces arise from the exchange of particles that carry interactions between matter particles. Weinberg's theory predicted specific particles responsible for the weak interaction with well-defined properties. These predictions were not vague. They were precise enough to guide experiments and test the theory rigorously. The eventual discovery of these particles confirmed that the Standard Model's structure was fundamentally correct. Another major contribution was Weinberg's influence on how mass is understood within the Standard Model. One of the deepest puzzles in particle physics was why some particles have mass while others do not. Weinberg's work incorporated a mechanism that explained how particles could acquire mass without breaking the mathematical consistency of the theory. This idea became an essential part of the Standard Model, showing that mass is not an arbitrary feature, but a consequence of deeper interactions. Weinberg's role extended beyond proposing specific equations. He helped define the standards by which theories in particle physics are judged. He insisted on mathematical consistency, predictive power, and the ability to connect with experiment, even if that connection was indirect or delayed. These standards shaped the development of the Standard Model and influenced how physicists evaluated competing ideas. The Standard Model also benefited from Weinberg's clarity of thought and communication. His ability to express complex ideas in a clear and systematic way made the theory accessible to other physicists, accelerating its acceptance and refinement. Through his papers and later his textbooks, Weinberg helped train generations of physicists to think within the Standard Model framework. His influence thus extended far beyond his own research. Weinberg's contribution also had a unifying philosophical dimension. He believed that the apparent complexity of nature hides simple underlying principles. The Standard Model reflects this belief. Despite describing dozens of particles and interactions, it is built from a relatively small set of ideas and parameters. Weinberg's confidence in this approach encouraged physicists to look for deeper order rather than settling for descriptive models that lacked explanatory depth. Importantly, Weinberg did not claim that the Standard Model was the final theory of nature. He was keenly aware of its limitations, particularly its inability to incorporate gravity and explain certain features such as the values of particle masses. However, he saw the Standard Model as a crucial step toward deeper understanding. His work showed how far careful reasoning and symmetry principles could take physics, even if further unification remained to be achieved. The success of the Standard Model validated Weinberg's approach to theoretical physics. Predictions derived from the model have been tested repeatedly and with extraordinary precision. Each successful test reinforced the idea that the framework Weinberg helped build captures something real and fundamental about the universe. Few theories in the history of science have achieved such accuracy across such a wide range of phenomena. Weinberg's role in the Standard Model also reshaped the culture of particle physics. After the confirmation of electroweak theory, unification was no longer seen as a speculative dream, but as a proven strategy. This success inspired continued efforts to unify all forces and to search for theories that go beyond the Standard Model. In this sense, Weinberg's influence extends into the future, guiding research that is still ongoing. In the broader story of science, Steven Weinberg stands as one of the architects of the Standard Model. His work provided the theoretical foundation that brought coherence, precision, and unity to particle physics. Without his contributions, the Standard Model would lack its central structure and much of its explanatory power. Through his ideas, Weinberg helped transform our understanding of the universe, revealing that beneath the diversity of particles and forces lies a deep and elegant order. Steven Weinberg's contributions to science extend far beyond his technical achievements in theoretical physics. While he is best known for his role in shaping modern particle physics, his influence as a teacher, writer, and thinker was equally profound. Through education, writing, and philosophical reflection, Weinberg helped shape how science is taught, communicated, and understood, not only by physicists, but by society at large. As a teacher, Weinberg was deeply committed to intellectual rigor and clarity. He believed that physics should be taught not as a collection of formulas to be memorized, but as a logical structure built on fundamental principles. In his classrooms, he emphasized understanding over routine calculation. Students were encouraged to ask why a theory worked, what assumptions it relied on, and where its limits lay. This approach challenged students to think like scientists rather than passive learners. Weinberg's teaching style reflected his respect for students' intelligence. He did not oversimplify difficult ideas, nor did he hide the complexity of modern physics. Instead, he trusted that careful explanation and logical progression could make even the most abstract concepts accessible. This respect created a demanding but inspiring learning environment, one that produced generations of physicists trained to value precision and deep reasoning. Beyond formal teaching, Weinberg influenced education through his textbooks and lecture notes. His books on quantum field theory became foundational texts for advanced students. These works were not merely technical manuals. They reflected a coherent vision of physics as a unified enterprise. Weinberg presented theories as parts of a larger conceptual framework, helping students see connections between different areas of physics. His writing set a standard for how advanced science should be taught: systematic, honest, and grounded in fundamental principles. As a writer for broader audiences, Weinberg played a crucial role in communicating science beyond the scientific community. He believed strongly that the public deserved clear and truthful explanations of scientific ideas, even when those ideas were challenging. In his popular science books and essays, he explained complex topics such as cosmology, particle physics, and the nature of scientific explanation with remarkable clarity. He avoided sensationalism and resisted the temptation to oversimplify, choosing instead to guide readers patiently through difficult ideas. Weinberg's writing was distinctive in its tone. It was calm, direct, and intellectually serious. He did not attempt to make science entertaining in a superficial way. Rather, he treated understanding itself as the source of wonder. This approach appealed to readers who wanted more than inspiring stories. They wanted genuine insight into how science works and what it reveals about reality. As a thinker, Weinberg was deeply engaged with the philosophical implications of science. He reflected often on what scientific progress means and how it relates to human values. One of his most important contributions in this area was his defense of scientific realism, the idea that scientific theories describe real features of the world, not just useful tools for prediction. Weinberg argued that the success of modern physics makes sense only if theories capture genuine truths about nature. He also explored the relationship between science and meaning. Weinberg did not believe that the universe was designed to fulfill human hopes or purposes. Instead, he argued that meaning arises from our effort to understand the universe as it truly is. For him, science was not a threat to meaning but a source of it. the act of uncovering the laws of nature, even when those laws are indifferent to human concerns, was itself a profound achievement. Weinberg was known for his intellectual honesty. He did not soften his views to make them more comfortable or popular. Whether discussing science, philosophy, or society, he stated his conclusions clearly and defended them with reasoned arguments. This honesty earned him respect, even from those who disagreed with him. It also modeled an important scientific virtue, the willingness to follow evidence and logic wherever they lead. Another important aspect of Weinberg's thinking was his historical awareness. He frequently reflected on the development of science over time, analyzing why certain ideas succeeded while others failed. He understood that science is a human activity shaped by cultural and institutional factors, but he also believed strongly in its ability to transcend those limits through evidence and reason. This balanced perspective allowed him to critique science without undermining its authority. Weinberg also contributed to public discussions about the role of science in society. He spoke about the importance of scientific literacy, rational thinking, and evidence-based decision-making. In an era when misinformation and skepticism toward science were growing, his voice served as a reminder of the value of careful reasoning and disciplined inquiry. He argued that science is one of humanity's greatest achievements and deserves both support and respect. Importantly, Weinberg's influence as a teacher, writer, and thinker was unified by a single principle: clarity. Whether explaining a complex theory, writing for a general audience, or reflecting on philosophy, he sought to remove confusion and reveal structure. He believed that clarity is not a luxury but a moral obligation in intellectual work. Confused thinking, in his view, leads to false conclusions and weak understanding. Through teaching, Weinberg shaped how future physicists think. Through writing, he brought deep scientific ideas to a wider audience. Through reflection, he helped society understand what science can and cannot offer. These contributions ensured that his impact would last far beyond any single discovery or theory. Steven Weinberg's legacy as a teacher, writer, and thinker reminds us that science advances not only through equations and experiments, but through communication, education, and reflection. His life demonstrates that explaining ideas clearly, thinking honestly, and teaching responsibly are as important as making discoveries. In this broader sense, Weinberg did not just change physics, he helped shape the intellectual culture of modern science itself. Steven Weinberg's lasting legacy in modern science and human knowledge lies not only in the theories he helped create, but in the way he transformed how humanity understands the universe and the process of understanding itself. His work reshaped the foundations of physics, strengthened confidence reminded in the power of reason, and influenced generations of scientists and thinkers. Long after his passing, his ideas continue to guide research, education, and philosophical reflection. At the heart of Weinberg's scientific legacy is the demonstration that nature is deeply unified. By showing that the weak nuclear force and electromagnetism are two aspects of a single electroweak interaction, he confirmed a belief that had guided physics for centuries, that the apparent complexity of the world hides simple underlying principles. This achievement permanently changed how scientists think about fundamental forces. Unification is no longer seen as an abstract hope, but as a realistic and productive strategy for understanding nature. Weinberg's work also strengthened the Standard Model of particle physics, one of the most successful scientific theories ever constructed. The Standard Model has been tested with extraordinary precision and continues to describe experimental results with remarkable accuracy. Because Weinberg's ideas form one of its central pillars, Every successful test of the Standard Model reinforces his legacy. His influence is present in countless experiments, calculations, and discoveries that rely on the framework he helped establish. Beyond specific theories, Weinberg's legacy includes a powerful example of how science progresses. His work showed that major breakthroughs often begin as abstract ideas with little immediate support. The initial neglect of electroweak theory, followed by its experimental confirmation, demonstrated that patience and confidence in consistency are essential scientific virtues. This lesson continues to shape how scientists evaluate bold theoretical proposals, especially in areas where experimental testing is difficult. Weinberg also left a lasting mark on the culture of theoretical physics. He insisted on high standards of clarity, rigor, and honesty. He believed that a theory must be mathematically consistent, conceptually clear, and open to experimental testing, even if such testing lies in the future. These standards have become part of the professional ethos of modern physics, influencing how new ideas are developed and judged. His legacy extends into education through the many students he taught and the textbooks he wrote. Weinberg helped train generations of physicists who now carry his approach into their own research and teaching. His books remain widely studied, shaping how advanced physics is learned around the world. In this way, his influence continues through the minds of those who never met him but learned physics through his work. As a writer and public intellectual, Weinberg also contributed to human knowledge by clarifying the relationship between science and meaning. He argued that science does not diminish human values, but deepens them by revealing the true nature of the universe. His reflections encouraged people to find wonder not in comforting illusions, but in the reality uncovered by evidence and reason. This perspective has influenced discussions far beyond physics, touching philosophy, education, and public understanding of science. Weinberg's defense of scientific realism is another enduring aspect of his legacy. At a time when some questioned whether science reveals truth or merely useful models, Weinberg argued that the success of modern physics makes sense only if theories describe real features of the world. This position strengthened confidence in science as a genuine path to knowledge, not just a tool for prediction. His arguments continue to shape debates about the nature of truth and understanding. Importantly, Weinberg's legacy includes his intellectual courage. He was willing to challenge prevailing views, resist fashionable ideas, and speak openly about controversial issues. Whether in physics, philosophy, or public policy, he valued evidence over opinion and clarity over comfort. This courage serves as a model for scientists and thinkers facing pressure to conform or simplify complex truths. His influence also reaches into the future of science. The success of electroweak unification inspires ongoing efforts to develop deeper theories that might unify all forces, including gravity. Even where current theories remain incomplete, Weinberg's work provides a roadmap. Seek consistency, respect symmetry, and trust reason. In this sense, his legacy is not finished. It continues to shape questions that have not yet been answered. On a broader human level, Weinberg's life reminds us that knowledge is one of humanity's greatest achievements. He showed that the universe, though vast and indifferent, is intelligible. Through disciplined thought and collective effort, humans can uncover laws that govern reality at its deepest level. This message is especially important in a world often marked by uncertainty and misinformation. Steven Weinberg's lasting legacy in modern science and human knowledge is therefore multi-layered. He transformed physics, influenced how science is practiced and taught, enriched public understanding, and strengthened confidence in reason itself. His work stands as evidence that the human mind, guided by curiosity and honesty, can penetrate even the most hidden structures of nature. In remembering Weinberg, we remember more than a great physicist. We remember a vision of science as a noble human endeavor, one that seeks truth without illusion, embraces difficulty without fear, and finds meaning in understanding the universe as it truly is. That vision remains alive, shaping science and human knowledge for generations to come.